Okay, today we are going to start group theory. Okay, so after we finish group theory, we solve some problems. Okay, so groups. So what is the definition of group? So quickly I can say, suppose G is a non-empty set together with a binary operation star is said to be or is called group or is said to be group is called or said to be a pair G comma star is said to be group if they satisfy the following property. That is, if we take any three elements A, B, C in G, satisfy the associative property, that is A star B star C equal to A star B star C. That is, first we have to operate B and C, and then you have to operate A. This is same as first you have to operate A and B, and then operate C, you get the same answer. So this property is called the associative property, associative law. So this actually no need to write the closure property because we say it's a binary operation. So the star is a binary operation. So therefore the binary operation means it's a closure property. So binary operation means what? Star is a function from G cross G to G. That means what? If you take any element A comma B in G, is maps to A star B. So therefore the binary operation itself says it's a closure property. Okay, now the first property is associative property, and the second one is identity element exists. That is, if you take, okay, so there is a element E in G, and if you take any element A in G, such that A star E equal to E star A equal to E. Okay, so there is an element is satisfy this condition. Okay, the quantifier is order of the quantifier is very important. So first you write for every there axis E, that is totally different. That means what? For each, suppose you are changing the order of the quantifier. Suppose you are writing for every A in G, there axis E in G, such that A star E equal to B star A star E equal to E star A equal to A. Then this means what? Given any A in A, for the corresponding A, we have another element. So that means what? Each element we have an identity element. That is not true, but identity element is unique for the group. Therefore, the order of the quantifier is very important. So there is an element is satisfy the property A star equal to E star A for every A in G. So this called identity element exists, and this is called identity element. Okay, now the third property, inverse. That is, if we take any element A in G, for each element they have a unique inverse. Therefore, there exists a unique. This is a notation for unique. There exists a unique B in G, such that A star B equal to B star A equal to identity element. So this is called the inverse element exists, or existence of inverse element. Inverse element exists. Existence of inverse element, and this B is called inverse of A. Sometimes we write B is nothing but the notation A inverse. Okay, we denote the inverse is by A inverse. So a set with the binary operation satisfy these three property, then we say it's a group. Suppose the operation star satisfy the extra condition that A star B equal to B star A for every AB in G, then G is called abelian group. Then the group G is called an abelian group. An abelian group. The first of all, it should be group, and then if you satisfy the extra property A star B equal to B star A, then it stays an abelian group. Okay. Now the examples of groups are the standard example set of all integers. So example of groups. So the first standard example is set of all integers with respect to addition. We can add two integers, right? So here, with respect to usual addition, this form a group. It's not, it's not only a group, it's an abelian group, because a plus b equal to b plus c. Okay, so this z comma plus is an abelian group. Again, if we take a set of all rational numbers with respect to addition, set of all real number with respect to addition, set of all complex number with respect to addition, or if you take rational numbers, you remove 0, that is q star. With respect to multiplication, again is a abelian group. Or you can take r star, you are removing 0 from r with respect to multiplication. Or if you take the complex number, you are removing 0, that is c star with respect to multiplication. These are all abelian groups. But if you take the matrix, if you take the square matrix, if you take the square matrix set of all m by n, so mn of r. So this means set of all n by n matrix over R with respect to addition, this form an abelian. But if we take set of all invertible matrices that form a group but not an abelian group. So that is, if we take set of all invertible matrices, that is we denote G L n of R. That is general general linear group of n by n. So what is the definition of this? Set of all matrix A whose determinant is not equal to 0. So we are collecting the invertible matrices. That is, we are collecting the matrices which determinant is not 0. Now this set with respect to matrix multiplication dot form a group is a group, but is not an abelian group. But not an abelian group, because in general the matrix does not satisfy the commutative property a into b equal to b into a. Okay, so it's not okay, but group but not group, but not an abelian group. This is the first example, or you can take this is one of the examples of non-abelian. Okay. Now, if we take the finite group, there are some. These are all infinite groups. So when we say a group is infinite, if the group contains infinite many elements, then we say it's an infinite group. If the group contains finite number of elements, we say it's a finite group. Now, the examples of finite group, if you take G equal to, just I take -1 plus 1. So now this set form a group with respect to multiplication. Therefore, G comma usual multiplication is a group. Is a group. So I into I, sorry, 1 into 1, 1, 1 into -1 is -1, -1 into -1 plus 1. So this is usual multiplication. So this is an abelian group, even is an abelian. So not only group, it's an abelian. This is a first, this is one of the example of finite group. Suppose if you take another group G, is contains -I plus I -1 plus 1. Now again with respect to multiplication, this G comma star or multiplication is a group. Even is an abelian group. Okay, what is the condition? That I square should be -1, the complex number. This is one of the example of finite group. So the another example of finite group is, if you take only singleton 0, that is also a group. So now the group is, next one is Z suffix n. So that is set of all integers modulo n. So this contains the element 0, 1, 2 up to n minus 1. So here addition is modulo n addition. So modulo n addition means what? Suppose for example in Z6, if you take Z6, suppose you are adding 3. 3 is an element of this. Suppose you are adding 3 plus 3, your answer is 6. So, but you take modulo 6. We take modulo 6 means what? We have to remove all the multiples of 6. Therefore, we get 0. Suppose we get a 2 plus 4. 2 is an element in Z6. 4 is an also element in Z6. Answer is 6. But modulo 6 is 0. Therefore, 2 plus 6, sorry, 2 plus 4 is nothing but 0. So, in the group Zn, n is nothing but congruent to 0 modulo n. Therefore, this Zn with respect to this addition, so this is a circle, O circle, okay. So this is addition modulo n. This is also a group, and even this is an abelian group. Okay. The order of the group is n. So this is a very important finite group. So another important group is set of all bijection functions. Suppose we have a set. We take any set. Okay. Suppose let x capital X be any non-empty set. Be any non-empty set. Now there is no operation on the set x. This x is anything. Now we know what is the definition of bijection. So suppose we have function f from x to x. So when we say this function is bijective, it should be 1 1 and on 2. So when we say a function is 1 1, different element maps to different element. So what is the definition of on 2? If we take any element in the codomain, it has a free image. Now we are collecting the function. Set of all functions from x to x is bijective. We are collecting the bijective function. We call the name for this set and take called a of x. Okay, that's nothing but set of all functions, bijective function from x to x. Now we have a group structure on the set a of x. With respect to composition. So this O means composition of two functions. So it's a group. That means what? Composition of two bijection function is bijection function. Inverse of a bijection function is bijection function. And then identity function is there. It's also a bijective function. Therefore, the set of all bijective function with respect to composition of function form a group, but not abelian group. But not an, this is very important example, not an abelian group. So that means what? If we take two function f composition g, in general not equal to g composition f. So composition of two function does not satisfy the commutative property. Okay. Suppose this x is any set. Suppose if you take x is a finite set. Suppose take the set contains n elements. Okay. So suppose the special case, if you take x contains only some n elements, we will call 1, 2, 3 and so on, some n. Any n elements, better I call 1 to 3n. So another way of writing this set is they denote I suffix n. That means first n natural numbers. Now if take x is finite set, then the a of x is nothing but we denote s suffix n. It's nothing but permutation group. We call as a permutation group. Permutation group on n symbols. Again, it's set of all bijective function, but it's a function from the finite set 1 to n elements to 1 to n elements. If we take any general set, we call a of x. If you take Sn means what? Is a set of all bijection function from n elements s to n elements s. Or sometimes called is and this is called actually symmetric group. This general a of x is called the symmetric group. This a of Sn also is sometimes called, because this is a special case, right? This also we call symmetric group, but in general we say the set of all bijection function from x to x form a group. That group is called a symmetric group. If you take finite set, that is called a permutation group, sometimes called a symmetric group on n symbol. Okay. Now how many functions we can define from n elements sets to n elements sets? Okay. That is, maybe I can say directly, what is the order, the order of a of x, where x is a finite set, or the order of, or the cardinality of the group is n factorial. So we can define n factorial bijection function from the n element sets to n element sets. These are all you should know. So suppose we are defining some 1 function. Suppose we are defining we have to define 1 function from a set to another set. Assume that both a and b are finite set. Okay, so a and b are finite set. That means it contains some finite number of elements. Suppose f is a function from this to this, then if f is 1 1, so when f is 1 1, provided the cardinality of a should be less than or equal to coordinate B. The coordinative domain is less than or equal to coordinative codomain, then it is possible to define a one-one function. So if and only if f is one, assume that both a and b are finite set. This is the first one. Suppose a is greater than coordinate of b is greater than or equal to coordinate of b if and only if f is onto. So suppose f is both one onto, that is bijective means domain and codomain have same number of elements in the case of finite set, not for infinite set. Therefore, how many bijection function we can define from n elements to n elements sets? We can define n factorial bijection function we can define. So again, here also what is the operation? This is composition. This Sn symmetric group with respect to this operation of function, composition of two function. So because everything is a domain and codomain is suppose f is a function of x to y, sorry x to x. Okay. If you take another function g, so f is a function of x to x. If you take another function that also is a function of x to x, now take the composition g composition f is also a function from x to x. How we defined our composition? We at a point g composition f of, if we take any small x, we define this nothing but g of f of x. This is a composition of two functions at a point. Okay. Okay. So this group is a group, but it's a non-abelian group. It's non-abelian. Okay. So for example, if you take a special case n equal to 3, that is S3. So S3 contains 3 factorial elements, that is 3 factorials. There are 6 functions from I3 to I3. So what are the 6 functions? I can simply write E. E means what? Identity function. So a set contains, so this is X, this contains 3 elements, 1, 2, 3. And we have a set X that also contains 1, 2, 3. Now how many bijection function we can define? So that is a list. So that is 1 goes to 1, 2 goes to 2, 3 goes to 3. This is a one function. Usually we call E. Okay. So suppose I am writing 1 goes to 2. That is 1 maps to 2, 2 maps to 1, but 3 is fixed. That means 3 goes to 3. So what is the meaning of these 1, 2 is a cycle notation. So that means what is a function is maps 1 goes to 2 and then 2 goes to 1. So that is a notation just 1, 2. But 3 is missing here. That means what? 3 goes to 3. And if you write 1, 3, it's nothing but again is a function. Its map 1 goes to 3, 3 goes to 1, 2 is fixed. So 1, 2, 3. So 1, 3 means what? 1 maps to 3, 3 maps to 1, 2 maps to 2. That is the notation 1, 3. Is also a one of the adjective function. And if we take 2, 3, that is 2 maps to 3, 3 maps to 2, 1 maps to 1. So this is another function. This is also bijective function. So another function you can write 1 goes to 2, 1 is maps to 2, 2 is maps to 3, 3 is maps to 1. So this is another function. Now suppose if you take 1 maps to 3, 3 maps to 2, 2 maps to 1. So this is another function. So there are totally 6 functions in S3. So therefore coordinate of S3 is 6. 3 factorial is 6. Okay, so now we discussed what is group and then now next what is subgroup. When we say a subset of a group is said to be subgroup. Suppose we have a group G and H is a subset. Let H be a non-empty subset. Non-empty subset of a group G. Let G be a let H be a non-empty subset. We say that H is a subgroup. We say that H is a subgroup of G if H itself is a subgroup. For example, suppose this group is group with respect to star, with respect to the operation star is a group. If the subset also with respect to the same binary operation star form a group. It satisfies all the properties of group. But there is a characterization of group. H is a subset of G, is a subgroup. No need to check all the condition. If and only if we take any element A comma B in H. Okay, so if we take any two elements A comma B in H, implies A B inverse should be in H. So whenever if we take any two elements A comma B, A B inverse belongs to H, then H is a subgroup. So this is very important characteristic to check a set is a group subgroup or not. It's very important. No need to check all the group conditions. Okay, these are all very important thing. Okay, so please wait. So this is a calculation to check a set is subgroup or not. Okay, now maybe we'll discuss some examples. So in the already we discussed some groups. So what are the subgroups of the groups? So first we discuss EZ. Yeah, maybe I can write here. So examples of the subgroups of the groups. Suppose if you take the first example, suppose if you take the group G is set of all integers with respect to addition, then all the subgroup is of the form. If you take H, all multiples of n, where n is any natural number. Okay, so H equal to n is a subgroup. Okay, where n is any natural number. For example, all multiples of 2, all multiples of 3, all multiples of 4, all are subgroups. So these are all the only subgroups in Z. So where H equal to n Z is a subgroup of Z. Now this Z is a subgroup of Q. So there is a, we know that Z is a subset of rational numbers, and the rational numbers is a subset of real numbers, and real numbers can be viewed as a subset of complex number, right? So everything is a group with respect to usual addition. Therefore, this Z is a subgroup of Q. Q is a subgroup of R. R is a subgroup of C. Since subgroup is transitive, therefore Z is a subgroup of R as well as Z is a subgroup of C. Similarly, Q is a subgroup of R and therefore is a subgroup of C. Therefore, the subgroup is a transitive property. Okay. So in EZ, the only subgroups are NEZ, where n is any natural number. Okay. So where n is any natural number, either 2 or 1. If we take n equal to 1, you get a whole group. If we take n equal to 2, you get all multiples of 2. If we take n equal to 3, you get all multiples of 3. So these are all subgroups. And these are a relation between the subgroups. Now, in that symmetry group, if you take G equal to the symmetry group, the permutation group Sn with respect to function composition addition multiplication operation. Now what are the subgroups? There are so many subgroups. Now the standard subgroup is even permutation, that is we call A suffix n, or sometimes called alternating subgroups, alternating groups. Okay, so it's nothing but set of all even permutation. So I will say what is even permutation, odd permutation. So set of all even permutations. Okay. So I will say what is when we say a permutation is a even permutation, odd permutation. I will say. Suppose usually we call the notation sigma to denote the element in the permutation group. Either you can use sigma or tau or theta. We can use this notation to represent the permutation. Suppose if we take sigma in Sn, then this sigma, there is a theorem says this sigma can be expressed as a cycle notation. So for example, some A1, A2, etc., some AN into some B1, B2, etc., product of cycles. So disjoint product of cycles. So every permutation. So this is cycle notation. This notation is called cycle. So the length of the cycle is n. Therefore, this is called n cycle. And this is cycle, and length is m. Therefore, we call it a m cycle. Okay. So the theorem says, what is the theorem? If you take any permutation, every permutation, okay, every permutation can be expressed as a product of disjoint cycles. Can be expressed as a product of disjoint cycles. So the disjoint cycle is what? There is no element in common between any two cycles. So that is disjoint. Disjoint cycles. Disjoint cycles. Okay. So another, the corollary of the theorem is every permutation can be expressed as a transposition. So I will say what is a transposition? Nothing but the cycle is 2, then we call it a transposition. Okay. So permutation, every permutation, every permutation can be expressed, but not disjoint. But we can express a product of transposition. Can be expressed as a product of transposition. Product of transposition. Transposition. Okay. So transposition nothing but if a cycle length is 2, then we call it a transposition. For example, if you take the previous case, yeah, in this S3, so look at this permutation. This is a cycle. So what is the length? Length is 2. Therefore, this is called a transposition. And this is also a cycle. Cycle length is 2. Therefore, this is also transposition. So this also cycle of length 2. Therefore, this also transposition. But this is length 3. Therefore, we call it a 3 cycle. This also length 3. Therefore, we call it a 3 cycle. Okay. Now the theorem says if you take any permutation can be expressed as a product of cycles, disjoint cycles, or product of transposition. Now if you take this element, this is just a single cycle, right? 1, 2, 3. So we can write this as a product of cycles, product of transposition. What is that? This is a function 1, 2, 3. This can be written as actually 1, 2, 1, 3. This is a cycle of length 3, but we can write in the transposition product 1, 3, 1. So some books are used some other way. So maybe we will check why this is true. So we can write this actually cycle notation. These are all cycle notation, but there is another notation is there that is called permutation notation. So that means this 1, 2 is nothing but first we have 3 elements in the set 1, 2, 3, but 1 maps to 2, 2 maps to 1, 3 is fixed, that is 3 goes to 3, that is 1, 2. Okay, and this is 1, 2, 3. Here the second permutation cycle is 1 goes to 3, 2 is fixed, 3 goes to 1. Now what is the product of these two? So first we have to fix that 1, 2, 3 elements. Now here is composition, right? So composition, how we define? Look at this. So this is a composition of two functions. So here it's not a product, actually it's a composition. So in between these two functions we have composition. So first we have to operate what is on 1. So here look at this. Okay. So 1 goes to 3. What is 3 goes to here? 3 goes to 3. But sometimes some books are write this notation. They start from here. So 1 goes to 2, 2 goes to 2, therefore 2. Now start with the 2. 2 goes to 1, 1 goes to 3. Therefore this is 3. Now 3 goes to 3, 3 goes to 1. This is 1. Now this is a permutation notation. We can write in the cycle notation. You start from 1. 1 maps to this, 1 maps to this 2. Now 2 maps to 3. Now 3 maps to 1. This cycle is complete. Nothing but 1 to 3. Therefore 1 to 3 can be written as this. Actually sometimes usually we write, instead of writing this, first 1 3 and then 1 2, like this. I could write this 1 3 cycle into 1 2 cycle. But this cycle and this cycle contains the common element, namely 1. Therefore this transposition is not disjoint. Okay? Disjoint means what? It does not contain any common element. This theorem is very important. What is the theorem? In the symmetry group, any permutation can be expressed as a product of disjoint cycles, or any permutation can be expressed as a product of transposition. So transposition nothing but 2 cycles we call 2 cycle. Okay, so 2 cycle we call transposition. Okay, generally the length of the cycle is called n cycle or n cycle. Okay, so now we define what is the even permutation, what is odd permutation. Okay, so the number of transposition in the product, if it is even, then it is called even permutation. Okay, so that is, suppose we say sigma is even. So when we say a permutation, even permutation, if, so please wait. Okay, so now when we say a permutation is even permutation, there are 2 definitions, but everything is equivalent. So if the say permutation sigma is even, if sigma can be expressed as a even number of transposition. Okay, can be, sigma can be expressed, because we know the theorem that every permutation can be expressed as a transposition. If it is even number of transposition, then we call this a even permutation. So sigma can be expressed as an even number of transposition, even number of transposition, and we say it's a even permutation. So look at the examples in the previous thing. Now look at this 1 2 3. Now 1 2 3 can be written as product of 2 transposition 1 3 into 1 3. That is the number of, this is 1 transposition, this is another transposition. Therefore total 2 transposition. 2 is a even number. Therefore this permutation 1 2 3 is an even permutation. But if you take this case 1 2, this 1 2 itself is a transposition. Therefore we have only one transposition. Therefore 1 comma 2 can be written as product of transposition just 1 2. So we have only one transposition. Therefore this is a odd permutation. The last one 1 3 2, again we can write is a product of 2 transpositions, 1 2 into 1 3. So even this is one transposition, this is another transposition. If you take the product, this you will get 1 2 3, oh, sorry 1 3 2. Therefore even number of transposition, therefore it's a even permutation. Okay, so a permutation is even, then that permutation can be expressed as even number of transposition. Otherwise we call it a odd permutation. Okay, that is, if sigma is odd permutation if sigma can be expressed as an odd number of transposition. Odd number of transposition. Odd number of transposition. Now we are collecting only the even permutation. That form is subgroup. That subgroup is called alternating group. So that is called, we denote A suffix n is nothing but set of all even permutation. Set of all even permutations. Even permutations. We denote that is an. This form a group with respect to that same operation composition. That group is called a symmetric group. So this an with respect to that composition form a non-abelian group, and this group is called alternating group. That's why we call A alternating group. Alternating group. Okay. This is an important subgroup of the symmetry group. This AN is a subset of SN. Okay. And this is a subset of this one. Now, what is the order? What is the cardinality of how many even permutations are there? It's nothing but cardinality of AN should be n factorial by 2. So in the symmetry group Sn, if you take this is suppose Sn, then half of them should be even permutation, half of them should be odd permutation. Okay. So therefore half of them are even, therefore is half is n factorial by 2. So this is the cardinality of An. Okay. So this An is a subgroup of Sn. So now next we definition for a normal subgroup. Okay. When we say a subgroup is said to be normal, so before that we have to define coset. Okay, anyway, we can define using definition. Suppose let H be a subgroup. Let H be a subgroup of a group G. We say H is a normal subgroup. H is a normal subgroup of G if we take any element A in G and any element H in H, the product AH A inverse, or if we take G for any G in G, for any H in H, GH G inverse should be in the subgroup. If this has happened, then we say H is a subgroup, sorry, normal subgroup. Okay. So for example, if you take the matrix group, so example, so we know that already the set of all invertible matrices, that is our G, is the G ln of R. So G ln of R means what? Set of all n by n matrix, set of all matrix A whose determinant is non-zero. So this collection form a group with respect to matrix multiplication. Okay, we know that G with respect to matrix multiplication form a group. Now here we have a subgroup I am taking, so that is set of all matrix such that the determinant is 1. We are collecting the matrices whose determinant is 1. Usually we call the matrices S ln of R, special linear groups. S means S special linear group. It's very important subgroup. So we can easily show that this is a subgroup. Why this H is a subgroup of G? If you take any two matrices A comma B in H, what we have to show? We have to prove that A B inverse should be in H. But we know that A is in H, therefore what we know? Determinant of A is 1. And B is also we take from B, therefore determinant of B is also 1. Now what we have to prove? We have to prove the determinant of AB inverse also 1. So by the definition of properties of determinant, this is nothing but determinant of A into determinant of B inverse. But determinant of A is 1 and determinant of B is nothing but 1 by determinant of B. Already I said that determinant of B inverse is nothing but 1 by determinant of B. Again, we know that determinant of B is also 1, therefore we get 1. So whenever the matrix determinant is 1, that matrix should be in the H. Since the determinant of AB inverse is 1, therefore AB inverse belongs to H. Therefore, H is a subgroup. H is a subgroup of the vertical matrix G. Now we have to prove that H is a normal subgroup. That means what we have to prove? If you take any matrix A from G And if you take any other matrix B in H, what we have to prove? We have to prove A, B, A inverse. We have to prove A, B, A inverse should be in H. That means what we have to prove? We have to prove the determinant of this matrix should be 1. So apply the properties of determinant. This is the determinant of A into determinant of B into determinant of A inverse, but determinant of A inverse is nothing but 1 by determinant of A. Since determinant of A is a non-zero number, therefore we can cancel determinant of A. Since we take B from determinant of B, therefore implies that what we know, determinant of B should be 1. Therefore determinant of B is 1, this is determinant of A cancel, we get to 1. Therefore determinant of AB, A inverse is 1 by the definition of H, AB, A inverse should be in H. Therefore we start with the arbitrary element A in A, B in B, we satisfy these two. Therefore H is a normal subgroup. H is a normal subgroup of G. Therefore, this is very important normal subgroup in the matrix group. If we take set of all invertible matrices, then the normal subgroup is set of all matrices whose determinant is 1. Suppose if we take some other number instead of determinant is 1, if suppose if we take 2, then this is not a subgroup. Why? Because the identity element, identity matrix, we know that the determinant of the identity matrix is 1. But here we are collecting determinant is 2, therefore this set does not contain the identity matrix, therefore this does not form a group. Group means identity element should be there. Okay, therefore, if you take the determinant is 1, that is the only way this form a subgroup. If you take some other number here, this will not be a subgroup. Okay, therefore this H is a normal subgroup of this set of all invertible matrices. Now our so already we know that the AN, the even set of all even permutation is a subgroup of Sn. Okay, then this also normal subgroup. So normal subgroup, first you have to check the subgroup condition, and then we have to take the another condition, normal condition. So it's a normal subgroup. Okay, that is trivial. So if you take how to prove this a normal subgroup, if you take any element here, you take any element here, the product. Suppose you take some sigma in Sn. Suppose I take some tau in An. So what we have to prove? Sigma tau, sigma inverse, we have to prove this is in An. That means what we have to prove? This product, this composition should be even. Already we know that tau is even because tau is an element in An, therefore tau is a even permutation. Now what about this sigma? Sigma may be even or odd. If sigma is odd, sigma is also odd. Therefore odd plus even. Therefore totally we get even. So all the case, if sigma is even, suppose this sigma is even, okay, then automatically sigma is also even, and this tau is always even. Therefore everything is even. Even plus even plus even is even. Suppose sigma is odd, but tau is always even because we take from An. If sigma is odd, then sigma is also odd. Therefore odd plus even. Therefore we get even number of transposition. In that case also we get the product is even permutation. Therefore this An is always a normal subgroup of Sn. A very important thing. Okay, so therefore this we should just check this condition. So normal subgroup means if you take any element in the group, any element in the subgroup, we have to check this G inverse should be in H. Okay. Now, so we define everything, but not all subgroups are a normal subgroup. For example, if it is abelian, that is another result. So the result in a abelian group, every subgroup is normal subgroup. Every subgroup in an abelian group is always normal. Any subgroup in the abelian group is normal. It's always satisfied. It's very important property. Okay. But all subgroups are need not be normal, but every normal subgroup is subgroup, but subgroups are need not be normal. Okay. We will discuss, we will give some examples. Even if you take the Klein 4 group, all these are normal in A4, but not normal in S4. Anyway, we will discuss later. So maybe I can write the result. Not all subgroups are normal. Okay. Okay. The next definition is cyclic group. So when we say a group is said to be cyclic if it is generated by a single element. So cyclic group. A group G comma star is said to be cyclic. Is said to be cyclic if there is an element A in G such that this G is nothing but every element of G is a powers of n, that is set of all A power n such that n in Z. Or we can write this notation, this to A. Okay, this A is called generator. A is called a generator of the group. Generator of G. Where what is this A power n? Where A power n means what? We have to operate A star, A star, A n times. So depending upon star, we have to put what is A power n. So this is n times. So a group is said to be cyclic if you take any element B of G, B is a power of single element. So that is one element generates entire group. The group is called cyclic group. For example, take integers. So that is a standard example. The infinite. Okay. So example, if you take, I am taking G is the 2-point set -1 +1. Now this is a group with respect to multiplication. We know that. Now this group is generated by -1 because if we take any element in G can be expressed the power of -1. -1 can be written as -1 power 1. 1 can be written as -1 power 2. Okay. Therefore, every element can be expressed the power of the single element -1. Therefore, -1 is generated. Therefore, this is cyclic group. But any group, the identity element is not a generator. Since this 1 is the multiplicity identity of the group G, it's not a generator. The identity element generator only in the trivial group, singleton, not further. So therefore, this is cyclic group. Generated by -1. Now, if we take another finite group, suppose we take G is -i, I, -1, +1. Now, this is a group with respect to multiplication. Now, this G is spanned by I because every element of the group can be expressed the power of this I. So, I can be written as I power 1. Minus I can be written as I cube because I square is -1. We know this. So, multiply I both sides, I cube is -I. Now, the next element -1. So, -1 is nothing but, so +1 is I square. Therefore, -1 should be here I square, I power 2. I power 2 is -1. 1 is I power 4. Therefore, every element of the group can be expressed a power of a single element, namely I. Therefore, I is a generator. Not only I, we can write every element of G is a power of -I. Why? Because we can write I is nothing but minus I power, what we can put? We can put, so I square is minus 1. So we need I. So therefore, I cube. What is I cube? I cube is minus I. So first you write right. Right. Okay, I will come later. So minus I can be written as minus I power 1, and then 1 can be written as minus I power 4 minus 1 I think minus I power 2, because minus cancel, I square is minus 1. Now the power 1 is come, 2 is come, 3 is come, therefore automatically this is 3. So what is minus? I think, oh yeah. So minus I power 3 is nothing but minus I3. But my I3 is nothing but minus I minus minus plus I. So therefore every element of G can be expressed a power of minus I. Therefore minus I is also a generator. Therefore in this group there are 2 generators. You can take anything. Anyway, this is cyclic group. G is a cyclic group generated by I or minus I. There are 2 generators. This is a finite cyclic group. So the next one is infinite cyclic group. If we take our group G is set of all integers with respect to usual addition. Okay. Now here I'm saying that this G or Z is generated by single one. So here operation is addition. So by the definition we say A power n set of all A power n such that Z. I already said that A power n is nothing but A star A star. Okay, n times. Here star is a plus, therefore A plus A plus A n A. Okay, so we take any element in Z can be right as a multiple of 1. For example, if you take n can be written as n into 1. Or if you take 5, 5 can be written as multiples of 1, that is 5 into 1. Or if you take minus 10 can be written as minus 10 into 1. Therefore, this 1 is a generator. Not only 1, if you take minus 1, this minus 1 also is a generator. That means what, if you take any integer, can be right multiples of minus 1. For example, even if you take 5, 5 can be written as minus 5 into minus 1. Anyway, this should be an integer. So this is for addition, multiplication. So for addition group, we say NA such that N in Z. So a group is, every element is of the form multiples of A, then A is a generator of the group. Now clearly this Z have only 2 generators, namely 1 and minus 1. Okay. So Z is a cyclic group. This is very important cyclic group. Z is a cyclic group generated by 1 and also generated by minus 1. And there is, okay, once we discuss what is isomorphism, homomorphism, we say there are only one infinite cyclic group, namely Z. If we take any other cyclic group, it should be isomorphic to Z. Now, another important example of cyclic group is Zn, integer modulo n. So I already said Zn. So n is any number 1, 2, 3 up to n minus 1. It's always cyclic group. Now, what are the generators? The generators are this Zn is generated by K. Where what is K? Where the K satisfies the condition GCD of K comma N is 1. If GCD of K comma N is 1, then K is a generator of this one, and K should be positive number, should be less than, what is the condition on K? K always lies between 1 and n. Okay. So for example, if you take Z5 or Z6, now what are the integer, what are the numbers which are relatively prime? Or relatively prime means what? If GCD is 1, then we say K and N are relatively prime. Now, if you take the GCD of 1, 6 is 1. Okay, therefore 1 is a generator. Since GCD of 2, 6 is 2, but therefore this is not a generator. 2 is not a generator. If you take GCD of 3, 6 is 3, again 3 is not a generator. Take GCD of 4, 6 is 2, again 4 is not a generator. If you take GCD of 5, 6 is 1, therefore 5 is a generator. So another generator is 5. That's it. The Z6 contains 0, 1. 0 is never generator, not a generator of any group. So other elements are 1, 2, 3, 4, 5. So the only generators are 1 and 5. Okay. So using this one, we can 1. So if we take 1, 1 plus 1 is 2. 2 plus you can add 1 3 times, you get 3. If you can add 1 4 times, you get 4. You can add 1 5 times, you get 5. You can add 1 6 times, you get 0. So we get the entire space. Now same thing here. We have 5. 5 plus 5 is 10, but 10 modulo 6 is 4. And then 15. 15 modulo 6 is 3. Because 15 means we have to remove 12, we have 3. And then 18. So what is the next one? 20. So 20 minus 18 is 2. And then 25. 25 minus all multiples of this one, we will get a 1. 60 is multiple of this one, therefore we will see. Therefore, you will get a entire space. So in general, Zn is a cyclic group. The generators are K, where GC of K, comma, N is 1. So therefore, maybe I can state here. So whenever a group have a one generator, we can say another generator. Okay. So that is, if A is a generator of the group, then the inverse, A inverse also a generator. So if A is a generator, of a cyclic group G, then A inverse is also generated. Also generator of G. Therefore, if we have any cyclic group, it will have at least two generators. Namely, if you know one generator, you can say another generator is minus 1. Now, the result is, if we take any infinite cyclic group, it has exactly two generators. So result 1 is very important result. If you take any infinite cyclic group, it contains infinitely many elements. Any infinite cyclic groups have exactly two generators. Have exactly two generators. But if you take finite cyclic group means some order is there. Suppose any finite cyclic group, so finite means there is an order. So finite cyclic group of order n has exactly pi of n generators. So this pi is Euler pi function. So I will say what is this pi of n. This pi of n is very important number. So exactly pi of n generators. So what is this pi of n actually? So pi of n is nothing but the cardinality of the set. The cardinality of the number of k which are relatively prime to n. So because all the k's which are relatively prime to n is the generators, now the cardinality is the pi of n. Now how to find this one is there is a formula. So we know that by fundamental theorem of arithmetic, given any number n can be written as product of prime powers. P1 power some alpha 1, P2 power alpha 2, etc. some P r power alpha. So any natural number can be expressed as a product of prime powers. This alpha i's are any non-negative number, but p1, p2, pr are prime numbers. Then the pi of n value is, you have to multiply first n into 1 minus 1 by p1 into 1 minus 1 by p2 into etc. 1 minus 1 by pr is very important formula. So for example, if you take a 10, so if n equal to 10, 10 can be written as 2 into 5. Therefore, here alpha L is 1, alpha 1 is 1, beta alpha 2 is 1. Anyway, so what is pi of 10? Is 10 into 1 minus 1 by 2 into 1 minus 1 by 5. So therefore, 10 into 1 minus 1 by 2 is 1 by 2. This is 4 by 5. And then 10 to 5 cancel, we get 4. Therefore, pi of 10 is 4. Okay. Now, then how many devices are there? So once you write the any number can be written as product of prime powers, there are so many definitions of that. This is an Euler phi function. Now, what is the number of devices? How many devices are there for n? So number of devices of n. Devices of n is nothing but just to write the product of prime powers, and then you got to add 1 to the all the powers. 1 plus alpha 1 into 1 plus alpha 2 into etc. 1 plus alpha r. So the number of devices of 10. For example, in the case of 10, so the power is 1 and this power is 1, therefore 1 plus 1, 2, and this 1 plus 1, 2. There are 4 devices for 10. What are the devices of 10? 1, 2, 5, 10. So only 4 devices. Okay, this formula is very important. So once you write, we have to write, we should know the factorization of any natural number. Now the theorem says, we take any finite cyclic group of order n, it has exactly pi of n generators. So already we discussed some example. Look at this second example. So what is the cardinality of, what is the order of the group is 4. Now what is pi of 4? Pi of 4 is 2. Therefore 2 generators, namely I into minus I. Got it? Yeah. Okay, so in the previous one, the first example, order of G is 2. What is pi of 2? Is 1. We have only one generators, namely minus 1. So this is very important thing. So maybe the question may be asked like that. This right? Yeah. So first they give the order of the group. Suppose G is a group of order 10. It is given. Now give the sum set, that is collection of all elements A in G such that A is a generator of G. Maybe they call some name or S or A something. The question they will ask, what is the cardinality of S? So there is another number of generators. So therefore number of generators is nothing but pi of 10. So pi of 10 we know the value 4. Okay, therefore the cardinality of the set is 4. Okay. Okay, maybe we stop now. Thank you.